So yes, let's continue with recursion. So first thing we're going to do is we're going to code, we're going to solve the following problem. Given a set, let's say of number or anything, set of anything, you want to compute all the possible subsets of that set. Okay, so you want to compute and return all the possible subsets of that set. And that thing has a name, it's called the power set. Okay, so given a set, you want to compute all the possible subsets of that set. So you, in other words, you want to compute power set of the given set. So let's, all of these things are usually more easier to explain in an example. So let's see let's see it on an example. So here we have a set with 3 elements, A, B, C, and you want to know what's a power set of that. In other words, what are all the subsets of that set. First of all, an empty set is a subset of every set. Okay, so we can start with an empty set. Then you have all the subsets that contain exactly one element, for example. So here we have a subset, one subset is A, then we have a B, then we have a C. Those are subsets of A, B, C. Then we have all the pairs, A, B, A, C, B, C. And finally, in this example, we have a set A, B, C. Okay, so hopefully you understand what a problem is. One of the reasons I picked this one is that I find at least I myself, I find a recursive solution to this problem more natural than iterative solution to this problem. Okay, and there's going to be another reason I'm going to mention at the end. So let's try to code this. All right, so hopefully understand your input is going to be some set, and output is going to be a all the subsets of that set. So a power set of the given set. Okay. So let's figure out what should be our output. So we want something like this. You want a set where each element of that set are another sets. Depending how you want to code it, you can also represent this as a list, what you're returning. Like you're going to have a 2D list where each element is going to be another list representing subsets, these elements of this power set. And actually, for my solution, and it will become clear shortly why I will use lists, because I will actually want to use slicing, and slicing slicing is very convenient, and you can do it on sets. Okay, so here's what so what do we want to code? We want to code a function power set. So let's say even input, I'm going to stick to a list. So this is going to be a list of elements, and I want to return a 2D list representing a power set of the elements in the list. Okay, so so in other words, what does this do? It returns all the possible subsets of L. Or small lowercase l, I guess I use lowercase l. Okay, so remember when we were saying when we are designing recursive algorithms that there are 2 questions that you should ask yourself. The first one is, when do you have solution trivially? When there is basically nothing to do? When do you know immediately what to return?
When you have an empty list?
Exactly, when we have an empty list. So if the length of the list is 0, we just return there's one possible subset. So we are returning a 2D list, and that only possible subset is an empty set that we represent as an empty list. So that's what we're returning. Okay, the only possible subset of that list is an empty set, represented here as an empty list. Okay. So that was question number 1. When do you know the answer? Immediately, when there's nothing to do but return the answer. All right. The second question is, how do you return, not how do you return, how do you, let me take my tablet.
Would another solution also be when the length of the list is just 1, so then it would just return that one element?
Is it really just one element? Let's code it. You can do it. You can do it manually for as many as you like, right? But you should also do it when the length of the list is 0, because otherwise, if you just do it when the length of the list is 1, you're missing a solution for that border case. All right.
Oh,
So, all right. So here, okay, so that's one set. Is that really the only thing we should return in this case?
And an empty set.
And an empty set, exactly. Okay, you can code it. But this is like a tip. Sometimes these are called base cases, these small cases that you code at the beginning. What they do, they help you when you're making recursive call. Eventually, hopefully, some function is going to return, because if at some point, if no function returns, you basically have de facto infinite loop, and you're going to have a crash because you're going to have too many functions on the stack. So these are the cases when we end up, we are doing recursive calls, and when we end up with a list of 0, 1 element, we return immediately the results, because that's when we know the result. You can code 1 or 2. Sometimes you need 2, depending what type of recursion you are. In this case, 1 is enough, but we could also have 2 like this. Okay. All right. So we solved the easy cases. And we can or not leave this case, but just because I didn't in the previous class, I'm going to remove it, but it's perfectly correct if we keep everything else the same and hard code the solution when there is 1. Okay, but let's look at now, what do we do? What's the second question? Is what do you do when you have more elements? Okay, so then you ask yourself, how do I express a solution? So let's say I have a list, a set. Well, now we're thinking on paper, forget about coding. Let's say I have a set with 3 elements, just numbers, 1, 2, 3. That's my set. And I want to compute a power set of that set. Okay, that's what I want to know. And we have seen what it is. Empty set, then a 1, then a 2, then a 3, then 1, 2, 1, 3, 2, 3, and then 1, 2, 3. Okay, that's what we want to compute. All right. And the strategy when you're designing this recursive solution is that you express the solution to the whole problem, big problem, well, big in our case is 3, in terms of a solution to a smaller problem. Okay, so what would be a smaller problem that you would consider here, for example? What's one example of a smaller problem?
After you remove one element from the set S?
Yeah. So typically, if you're out of inspiration, and often that's like the best thing you can do, you just imagine, what if somebody gives me a solution to everything but one element in the set, for example. So here I'm saying, what if somebody gives me a power set of everything excluding number 1? Okay, so let's say what we have. So let's say somebody gives you a power set of S minus this element 1. Okay, so basically of power set of this. Okay, and we know what that is. That is empty set, a 2, a 3, and then a 2, 3. Okay, so suppose we have a power set of everything except for one element. How do you now get a power set of the whole set? So we have all the subsets excluding 1. Okay, excluding number 1. How do we now get a power set of the whole thing? So I want now this. How do I now compute this? So given that I have that, how do I compute this power set of the whole thing S?
You take the possible combination of S.
Okay, but that's a definition of a power set, and you're going back to S. how do we use the fact? And that's not easy, right? That's like saying, let's compute all the combinations. But then the question is how? And I'm asking, okay, what if I give you this, all right? Then is there easier way than just saying compute all the permutations? Or
The one to every subset
every subset of what?
of if the given subset, if you add one, you'll have every subset of one. So the empty one becomes one.
Okay. First of all, exactly. So first of all of these are in my final power set, right? They are also subset of S. So first of all, I should copy all of these, the one that are already there. So first I copy what's already there. So because these subsets are all the possible, can you please, participants, let me try to mute you. There are people who are, all right. Those who want to ask questions, you can still unmute yourself. All right, so first of all, we copy all these subsets that do not contain one. Okay, they're also subsets of S. Okay, so we are done with all the subsets that do not contain one. Now we have to create all the subsets that do have one. And as was suggested by one of the students, how do you get them? You get them by looking at all of these subsets without one, and you just add one to them. Okay, so here, let's do that. We start with this one, we add one to it, we get a 1. Then we go this one, we add 1 to it, and we get 1, 2. Then we take this one, we add 1 to it, we get 1, 3. And we get this one, we add 1 to it, and we get 1, 2, 3. Okay, so what is the strategy? The strategy is if somebody was to give me a solution to power set of all the elements, excluding one element, then I can get, in a simple way, I can get the power set of the whole thing. First, I copy all the subsets that do not contain one, and then I create all the subsets that do have one, and I do that by taking every element, every subset without one and adding one to it, like we did here. Let's just code that. That's going to be 2 lines now that we know what to do. All right, so first thing we said, so, well, this thing saying, whenever you say, assume somebody gives me a solution to something smaller, that means you call recursion to compute it for you. All right, so we make a recursive call and we say, give me a power set of everything except for the first element of the list. That's why I want to use slicing, but you could also just remove some element of the list, of a set, if you want to use sets. So I say, I'm calling a power set of everything except for L of 0. All right, so I'm removing the first element of the list, and I store this in PPS. I call it for partial power set. That's this one here. Okay, so this thing here, this is my partial power set. Okay. And now I want to compute here a full power set of the whole S, full power set. All right, so what did we say we do first? First, a full power set, I want a full power set to have the same element as partial power set. So I copy them. All right, so hopefully you remember that this just copies, this creates a copy of this list. And my full power set now contains all of those elements that PPS has. Okay, so that was the first pass. Copy all the elements, all the subsets without L0. Let's, okay, so what does this do? That was this part when we were copying everything, all the subsets without one. So copy all the subsets without L of 0 into the final list, into the final subsets. Okay, what was the step 2? Step 2 is to go through all the sets in a partial power set and add L of 0 to them. Well, we know how to do that. We have a loop. Take items from partial power set. So it's going to be an empty set, then 2, then 3, then 2, 3. Okay. And then add that to final power set. I mean, add L of 0 to it and then add it to the final power set. So we want to add to the final power set what? Okay. I want to add, so I have a list just containing L of 0, and I want to concatenate it with list item. Remember, item is just a list for us. It's an empty list, then a list with a 2, then a list with a 3, then a list with a 2, 3. Okay, so this is a list, and this is a list, plus it's just going to glue them together. I'm going to get to you, Francoise. Oh, Francois, sorry, I don't know. Not very good in French. Okay, return PP, return full PS. All right, so let's run this and see if it is working. I mean, I hope you see that what we did is exactly what we discussed on the paper. Invalid syntax from for item in PPS. Thank you. That's why your hand was up. All right. So
also, you return FPSX instead of
okay,
FPS.
Thanks. Final power set. Okay, there you go. So let's run this. And let's see if we got what we wanted. Power set 1, 2, 3. L capital L. I don't know why I did this exact same mistake in a previous class. Use capital L in that spot. All right, there you go. We computed all the subsets. An empty set, 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Okay, so hopefully it is clear that we are really just translating what we were doing in paper, which was to first figure out when we have when we know the answer immediately, and then figuring out how to compute a solution to the whole problem, given a solution to a smaller problem, to a subset of your problem. Okay, are there questions about this? Okay, so let's figure out, so what do I want to do next? Okay, let me show you first. I want to show you how this runs manually, just so it doesn't look like it's some magic. So let's run it on the paper if you like. And so let's see. All right, so let's do it on a much smaller example. I don't even want to do 1, 2, where it is, here. All right, so let's say we are calling this power function. Let's say we have a call like this, okay? And the list really has only 2 elements, 1, 2, and let's see how it computes a power set. So it should result in an empty set, a 1, a 2, and 1, 2. Let's see how this recursion actually does it. That each one of these function calls does some work, so it's not some magic. All right, so this function starts running. The list L in this case is 1, 2. It doesn't have length 0, but immediately we have a function call that says the partial power set is, and I want to, and we have a function call to a power set where we send everything except for the first element. First element is a 1, so actually this call just sends the list. So list L in this call that is just about to start running has only 1 element, and that's a 2. So this one pauses and this function starts running. Its list has only 1 element. We come here, but it's still not 0. We come to this line and we have partial power set is, and we have a function call here. So this one is going to pause and it's going to call a power set. What list is going to send? Well, it's going to take this list, L of the function running. It's going to remove the first element. Therefore, you're going to end up with an empty list. So this function is going to pause, and this one's going to start running. Its list L is an empty list. So when we start running here, the length of that list is 0. So this function is going to return an empty list to its caller. Well, a 2D list where the only element is an empty list. Okay, and terminate. So this function terminates. All right. This function terminates, so this one can resume and returns the control to the caller. So this one can resume. But now it got PPS. It got it, and it's this, right? Because that was returned. So now it continues running here. First of all, we copy that into the final power set. We have the same list is a final power set. Okay, and then we execute this code. It says for item in PPS. So here's PPS. So item is this. Okay, one and only element of PPS. We come over here. It says take L of 0. List containing only L of 0, so it does this. L of 0, this L is 2, and concatenated with item. Item is an empty list. So when we do this, we end up with a list 2. Okay, so we are actually done because there's no more items in PPS. The loop is done, and it says, sorry, this is attached. This is added to the FPS before we are done. So what we have here is the final power set is this. Okay, so now we are done, and you actually see that you have it. A power set of this set 2 is an empty set and a 2. Okay, so we have that. Now this function terminates. It returns this to the caller that was waiting over here. So it returns an empty set and a 2. Okay. So this function with list 1, 2 was waiting over here for this partial power set. Now it has it. So partial power set is whatever this function return, which is an empty and a 2. Okay, so now we have a partial power set. Function was waiting over here. Now it can continue. This function can continue. We copy in the final power set, first of all, everything that was in partial power set. Then we execute this loop. This loop is going to go through the partial power set. Partial power set has 2 elements, so we're going to go through the loop twice. So we have first item is equal first element of this power set, which is this. Then it says take a list containing L0. L0 here is a 1. Okay, so we concatenate a list containing 1 and item, which is an empty list, and that's a list containing 1. And we add it to, it says append it to the final power set. So we append it here. After that is done, the final power set has a 1 there. Okay, we continue with the for loop. It says take the next item from PPS. Well, that's a list contains a 2. Okay, so item is a list that contains 2. We come over here, it says take the first element of list L. First element of list L is 1. So take a list with that element. Take item, item is 2, and concatenate these 2 lists. So we have that 1, 2, and then it says append it to the final power set. Okay, so we add it there. So 1, 2 is added there. Okay, we are done with the loop because PPS had only 2 elements. We are done with the loop. We come here, it says return final power set. So see what we got. We are done. And what was computed is indeed the power set of this given set. I hope you now see how this works and how actually these recursive calls compute this. Okay, so now that we did this, let's look at a couple of more examples of runs. And let me ask you, all right, so rather than we've seen this works on a smaller example, but let's look at the bigger examples. Something like this, 1, 2, 3, 4, 5, 6. All right, so lots of subsets. Let's look at something like this. What was my next example that I wanted to show you? Power set. Remember that a range function produces a sequence of, I don't know, let's say this sequence of 8 numbers or 10 numbers. And we can convert it into a list. And now these are elements 0 to 9, and we want to compute all the, and it did compute it, but there's so many subsets that actually you need 300 lines to present it, so it refuses to print. Okay, what about this? Power set, a list, range. I want you to give me a list with about 1050 elements and give me all the subsets. Okay, it crashed. Why did it crash? You learned it the last time. Some of the reasons for this. In fact, Python tells you why it crashed, that we exceeded maximum recursion depth. Remember, maximum recursion depth is telling you at some point of run of your function or your solution, recursive algorithm, what is the maximum number of functions running at the same time? Okay, so in the case, let's say when you have a list with about 1050 elements, or in general, when you have a list with n elements, what is the height of recursion of this solution? So we start with a list. Can you speak up?
About 1,000.
About 1,000 when list has 1,000 elements. But in general, when list has n elements, what is the height of recursion?
Was it n minus 1?
It's n plus 1. But in general, we don't care about this plus minus. We want rough estimate, right? Just so you know, well, it's great if you know exactly, but you typically just care what is the rough estimate, so you know how close you are to having too many functions on a stack and your solution breaking. But let's look at, and why is it n plus 1 or roughly n? Because notice here we are starting with a list with n elements, and then our recursive call removes only one element from the list. And you need to go all the way down to 0 elements of the list before a single return happens. So you start with a list of size n, then you call a list of size, then the call is made on list of size n minus 1, then a list of size n minus 2, then a list of size n minus 3, all the way down to 0. You have to get down to the list of size 0. Each call just removes one element. So at some point, you're going to have n plus 1 functions on the stack. Therefore, if your list has about 1,000 elements, it's going to crash because Python allows you about 1,000 functions at most on the stack. Okay, so that's a height of recursion for this function. So we know now what it is. Let me show you one last example. All right, so I want to run this on a list with only 50 elements. So really it shouldn't crash, right? It's only 50 elements. So in the worst case, you're going to have 50 functions on the stack. Okay. And I press enter here and it's blinking, blinking, working. And we sit here. Okay, so 2 questions. Why is this just blinking and waiting here? First of all, if you're just computing things, can you tell me when are we going to see the result? How long would we have to wait for this result? Or maybe you think something is stuck, is going to crash. how long we're going to wait? So now we're talking about the efficiency of this solution, right? So let's remember we are counting two separate things. First of all, when we're looking at, first of all, always correctness first. Second of all, in recursive solution, you need to understand that if you exceed the height of recursion, your solution won't be able to, your program won't be able to handle it. So it'd be good to be able to figure out what is the height of recursion, or here they call it depth of recursion that your solution has. And we realize for this one is n, but here we are not close to that. And then in terms of efficacy, how many operations you need to compute to compute what you need. And of course, that's related for how long you wait for the solution. So we have a correct solution. It shouldn't crash because we are not exceeding the height of recursion, or we are not exceeding the space we are given on the stack. So that only leaves that this is still computing. So how long, what is the running time? What's the number of operations, not the running time? What is the running time of this solution, and how long do you think we're gonna wait?
I think since it's doubling every time, it should be 2 to the power of n.
Exactly. So why 2 to the power of n? First, you have to ask yourself, you have to ask yourself, how many subsets is there? If I give you a set of n elements, how many subsets is there of that set? Okay, so in case of 50, how many subsets is there? We have seen in this example that when your set has 3 elements, there's 1, 2, 3, 4, 5, 6, 7, 8 subsets. So no matter how you compute your power set, no matter how you compute it, no matter what you use, the amount of time, number of operations is going to be at least the number of subsets. Because just putting a subset into a list is going to, putting one subset into a list is going to take you at least one operation, right? So if your list has, if your power set has million elements, you need at least million operations, right? So you need to understand how many subsets is there in any given set, right? So if the set has n elements, how many subsets are there?
Is it n factorial?
No. How many subsets is there in n? If you have a set of n elements, how many subsets are there? It's not n factorial. 2 to the n. I can explain to you why 2 to the n. It's 2 to the n. Okay. So the running time of this solution has to be at least. And see, it's computing so much, I need to stop it, right? Because it doesn't let me write even in this. Okay, so let me kill it. I hope it. Force quit. All right, force quit. Well, I think I had that here. Yes, okay. So the running time, the number of operations your solution is going to do, whether you want it or not, if it's correct, it's going to have to do at least 2 to the n operations, where n is the size of your list, at least 2 to the n operations, because your list, every power set of a set with n elements has at least 2 to, has exactly, not at least, it has exactly 2 to the n subsets. So you have to write each one of them into a list. Just writing 2 to the n things into a list takes 2 to the n operation. So it's at least 2 to the n. So let's see how much time we're gonna wait at least for that solution, except that I killed it. Okay, so this thing is doing at least on a small list, only 50 elements, you are doing 2 to the 50 operations at least. Okay, this doesn't tell us much, but let's say you have a really good computer, you can do million operations in a second, 1, 2, 3, 1, 2, 3. So this is how many seconds we're gonna wait. Oh, you can say, okay, this doesn't tell me much. How many minutes? This is how many minutes. Still, this doesn't tell me much. How many hours? Okay. Oh, this many hours. Still, this doesn't tell me much. How many days? Okay. Even this doesn't. 13,000 days. Even this doesn't tell me that much, but that sounds awfully a lot. 365, let's say 365, a number of years. We are going to wait 35 years, 36 years for this solution. Okay, so this is another reason I wanted to show you this, is because actually this is the first time you're seeing exponential solution. We thought, you know, I was showing you example where quadratic solution is way more slower than n log n solution. But that you see a difference. It was on list with million elements. This is when you were starting to see a difference. Here we have a list with 50 elements, and we would wait 36 years to get a solution. And there's no better solutions because simply whatever the answer I'm asking has that many subsets. So there is no better than exponential solution for this. However, I would like to tell you that there are problems for which there is no obvious. Here it's obvious that if number of subsets is 2 to the n, then I need to do 2 to the n operations at least. But there are many problems for which this is not the case, and yet, and I'm talking about thousands and thousands of fundamental problems, and yet the only solutions we have are exponential solutions. As you can see, they are kind of useless unless you really are working with small inputs, okay? So these problems, for most of them, actually, we don't know are exponential solution the only case possible, but the only solutions possible, but the conjecture is that they are. Let me give you one example, and I'm going to tell you what these problems are called. You're going to study this in computer science. So let me give you an example that a student in primary school can understand. An example of the problem for which we only have exponential solution. The problem sounds almost trivial, but the only solutions we have take exponential number operation. So say I give you n numbers. You can imagine that these numbers are like weights on the scale, right? You have one weight with a number that is 1 gram, another one 20 grams, another one 3 grams, and another one again with 1 gram, and so on. So you have numbers or weights, and your job is to just answer the following question, yes or no question. Can you split these numbers into 2 groups such that if you sum the numbers in one group and sum the number in the other, they are equal? Can you split them into 2? So can you split this number into 2 groups such that their sum is equal? Why was I mentioning weights? That's the same as saying I give you n weights. Can you put them on the scale such that the scale is balanced? It's the same thing. There is no non-exponential algorithm for this problem, or at least the only algorithms that all of humankind and all of history ever was able to come up with, the only algorithms we have are exponential. And for this, there is no obvious reason to be exponential like here. Here, just to write into the list 2 to the n elements, you need to do 2 to the n operations. Here, I don't need you to write anything. I just need yes or no to compute, to tell me what is the, I just need yes or no answer to this. Okay, so there's no obvious reason why it should be exponential, but the only solution we have is literally try everything. Try all the possible way to split numbers into 2 groups. But if you try all the possible way to split numbers into groups, that there is exponential in many ways to do that. Okay. So this problem called partition problem, it has a name. It's so-called NP-complete problem. There are, as I mentioned, thousands of its NP-complete problems. You may think this is only on theoretical interest, but imagine you're working anywhere in a company and some of the sub-problems that you need to solve is something like this. This happens all the time. These are fundamental problems. You better know that this is one of these difficult problems, that this is one of these problems that only has exponential solution, because nobody's going to wait 36 years. So you better be looking for approximation, not exact solution, what's available in that case, and so on. So you're going to be studying this. But also I would like you to know, curiosity, that this is related to these exponential problems, such as this partition problem, is the most important problem, open problem. We don't know the answer in all of computer science, and for most, for many people, consider this to be the most important problem, not only in all of computer science, but also in all of mathematics. And the question is P equal to NP? So this is completely open. Nobody knows. Many researchers are working on this. Nobody knows the answer to this. What this basically is saying in a layman language, and you're going to learn specifically what it means, is it true that these problems, like what I just explained to you, partition problem, is it true that they only only have exponential solutions, that they do not have polynomial solution? What do we mean? What would be a polynomial solution? Things that you have seen, like a quadratic n to the constant, that's a polynomial. Even n to the 100, that's a polynomial. So n to the any constant, do they have n to the any constant solution? What you don't want is constant to the n, that's exponential. Okay, so the question is, do these problems have polynomial solutions? This problem is P equal MP, is tied with $1 million prize and lots of fame for those who prove it or disprove it. Most researchers believe the answer is no, that they are not equal. In other words, that these problems, such as partition problem, do not admit that polynomial solutions do not exist. Okay, so that's kind of window into what you're going to see in the future, and first time seeing solutions that are exponential, which in this case, the one I presented to you is a power set. Okay, so that's it for that. The next example, unless you have questions, does somebody have a quick question? Because I want to move to the next example. Okay, so the next is going to be something much more familiar, something that all of you know, which is computing a power, like 2 to the 5, 2 to the 100, stuff like this. This is such a fundamental problem, even in programming, that Python has that function to compute a power. Python has a function even in built-ins. Remember how you find out what's in built-ins? You see that a power function is there. You can ask Python how to use it. And it tells you, you give me a base and give me an exponent, and I'm going to compute base to the exponent. So 2 to the 4, it's telling you it's 16, I don't know, so on. So we're going to write our own power function. My power, I'm going to call it my power. So what do I want this function to do? Is to compute x to the n. So okay, so x is going to be my base. So what do I want to happen is that, you know, if I call my power 2 to the 4, it also gives 16, right? So I want to design a function that does that. Okay, so first of all, given an x and given an n, how do we compute x to the n? Like in English or in math?
We multiply x n times.
Exactly, but not really. I mean, yes, but there is a but, okay? Here's a but. There is assumption. Your solution, and the only solution that, in fact, we know how to do, you making an assumption on n. So what we need to know is the domain of what we are solving. Because if we do something like this, yes, indeed, 2 to the 4, we know how to do this. That is 2 times 2 times 2 times 2. Okay, you do 4 times 2. However, what about this? 2 to the 2.5. Already, in fact, I don't even know how to do it. Well, maybe we know this one because, you know, that's 2 times 2 times 2 to the 0.5, which is actually square root of 2. But still, this implies already something way more complicated, which is that we know how to compute square root, all right? But not to mention that, you know, if you don't specify what domain it is, it could be something like this, which we have absolutely no idea how to do. At least I have no absolutely idea. Well, I guess I can learn, but I don't know how to do it right now. So we are not trying to solve this. So our domain is we making some assumption. So we are making an assumption, first of all. So what do we do here? We're making an assumption that n is an integer. Is that the only assumption we are making?
Positive integer, otherwise it would be dividing it by.
Exactly. Positive or rather non-negative. There is no reason not to assume that n is 0, right? X to the 0 is 1, right? So we need indeed, so here, let's say n is an integer. We already decided then x can be anything, float. And we are returning, not float, we were not using this. We were saying if it can be anything, we should put number. That's how we decided to do this number, these type contracts. So what are our preconditions, just so we make sure we know what we're solving? Preconditions is that n is non-negative integer. All right. Is there anything else we are assuming or we need to assume? There is one other case where.
Isn't it if n is equal to 0, it's always equal to 1?
But then there's nothing, there's no problems if that's the case, right? You just return 1. When n is equal to 0, you just return 1. But I'm just saying that we are making another assumption. Otherwise, you're going to crash or return nonsense. What case would that be?
X is non-negative.
That's also true, actually. Well, not really. If x is non-negative, we have to keep track if it's odd, n is odd or even, and you're right. So let's do that one as well. X is non-negative, just so we don't have to keep track of that non. And yet there's still something missing.
0 to the 0.
0, 0. X cannot be, we cannot have that both x and n are 0. This is not defined. Okay, so this is undefined. This is wrong. Mathematically, this is undefined. You have to compute limits and stuff like this. Okay, this is undefined. What Python is giving you here is wrong. Okay, so another thing, we are assuming that we don't have at the same time that both x and n are 0. Okay, so let's, okay, now that we agree on this, we are ready to code. What are those two questions? We have those two questions. The first one is, when do you know immediately answer? If we exclude it here, x equals 0 and n equals 0, excluded. Okay, so when do we immediately know the answer? When there's nothing to compute?
When
Can you repeat?
When n is 0?
Exactly. When n is 0, given all our assumptions, we can safely return 1. All right. So what was the question 2? How do you express, so I'm putting this in comments, we are now thinking of it mathematically. We are computing x to the n, and I'm asking you, how do you express this in a term of solution to a smaller problem? And typically we were saying, okay, somehow remove 1 or make it 1 smaller or something like this. So how do you express x to the n as a solution to as doing something, assuming that somebody gives a solution to a smaller problem? So how do you express this in terms of solution to a smaller problem?
Can you multiply x to the n minus 1 times x?
Exactly. Yeah. So okay, so this is x times x to the n minus 1. It's like x to the 1 times x to the n minus 1, because, you know, you add up the exponents and you get n back. So we are basically done. You copy paste that, return x times, and this is that x. You don't need to the 1. And then we call our recursive function to compute that. Okay, x to the n minus 1. So let's do that. Let's see if it's working. So what did we see here? 2 to the 4. Python told us my power, that's 2 to the 4. It seemed to be working. Let's try something bigger. 5 to the 100. That seems to be working. My power. Let's do 7 to the, let's say 1030. And this one crashed. Okay, so it's working correctly. But when n is 1030, it crashed. You get by now familiar message, maximum recursion depth exceeded. So why did it crash? What's the height of recursion of this function? You should just look at recursive call. N calls n minus 1. So what are the key things you're looking at? By how much does the input goes down to? So we're starting by n, it goes down by 1, and we need to get down to 0. That's when we start returning, you see? This one is just recursive call. So we're going from n minus 1, minus 1, minus 1 down to 0. So what is the height of recursion?
n plus 1.
N plus 1, exactly. So that explains to you why for 1030, n is 1030, so the height of recursion is 1031, but that's more than Python allows you to have for the height of recursion. Okay, so you're going to end up trying to put more than 1,000 functions on the stack at the same time, and the call crashes. Okay, so in this case, we are going to go back and see, okay, can we do something about this height of recursion? Okay, so where are we making recursive calls? It's over here. And it was based on this equation. Okay, is there more fair way to divide the work? Again, going back to what we were discussing the last time in class. If I'm asking 2 students to do work, this one is doing x to the 1, so nothing. And this one is doing, in case of, what did we have here, 10,030, this one is doing x to the 10,029. So multiplying x 10,029 times. So that doesn't seem like a fair division of work. So is there a better way or another way? So whatever way you find to express a solution in terms of smaller solution should work, as long as that expression is correct. So what's another way to express x to the n?
Could we kind of do the same thing? X to the n over 2 times x to the n over 2?
Exactly. X to the n is also equal. You just use a different equation if you like. X to the n divided by 2 times x to the n divided by 2. That's our strategy 2. X to the n minus 2. So this was our first strategy. This is our second strategy. So we just coded the first strategy. Let's code the second one. We just code what's here, right? So we do, instead of n minus 1, we're going to do n divided by 2 times that. Okay. Let's first see if it's working before we test it on the my power 2.4, because before we tested on bigger examples to see if we improve the height of recursion. But in fact, already on 2 to the 4, it crashes, and it even tells us you're exceeding a maximum depth of recursion. Okay, so it's crashing on a tiny number. Why is it? Why is it crashing on 2 to the 4? Let's see what we're doing. Okay, we start with n is 4. We come here, we are calling it on 4 divided by 2, it's 2. So we are doing x to the 2. So far, so good. We come here, n is 2. It's not 0. We come here, it says, okay, divide 2 by 2, and that's 1. So you need to compute, you call this function x to the 1. We come here, n is 1. It's not 0. Therefore, we don't do this part. We come here, and it says x is 2, n is 1. We do 1 divided by 2, we get 0.5.
Is it because it should be integer division?
Yes, but let's first even understand why did this crash. First of all, 0.5 is, we are already
never
not,
Zero.
sorry?
It's not reaching zero.
Not gonna hit zero ever.
Exactly. Exactly. So we go from 0.5 to 0.25 to 0.125 and so on. And all of these function calls will be pushed on the stack. Eventually, you're going to crash the stack because basically this is infinite loops because we never, as one of two students told us, it never goes down to zero, but it's only when we get down to zero that we are returning something, that we start returning something. So we are making basically, we would have made infinitely many recursive calls, except that Python crashes before that happens. Okay, so the correction is we should do integer division. Okay, let's do integer division. All right, we do integer division. It doesn't crash, but the solution is now incorrect. Okay, why do we get incorrect solution?
Because when you remove the decimals, you lose precision.
Yes, and in this particular case, actually, more importantly, let's see, actually, let's go back to this equation here. This equation, our first solution, this was our first solution. At least mathematically, this was correct. Okay. This one is not even correct. This one is only correct when n is even. Okay, so this is true when n is even. This solution is incorrect when n is odd. So we were first of all working with incorrect, so mathematically incorrect solution. So first of all, let's fix that. Okay, and why did it, and if you now go back here, you can say, wait a minute, but n for n is even. Yes, in that case, this formula is correct. But you are making a recursive calls and you eventually end up with n that is not even. We start with a 4, then we end up with 2, then we end up with 1. So when we are making here, when n is 1, this formula is now incorrect, and therefore you get some nonsensical answer because now our algorithm ends up with an odd n. Okay, so we have to fix, obviously, our mathematical solution first. So this is fine when n is even, and we have to fix it when n is odd. So what do we have here? How do I fix this solution such that it's correct when n is odd? What do I do to fix this?
Can you kind of factor 1x out? And so then
not factor out. You need one extra n because see what happens when n is odd. You lose 0.5 here. Let's say n is 5. You lose 0.5 here. You lose 0.5 here. You need one extra n. So you just multiply. Sorry, not n. One extra x times x. You are missing x to the 1 because you lost it here a half and you lost here a half by doing integer division. So we need x times this. So this is the correct expression when n is odd. So for example, when n is 5, you get here x to the 2 times x to the 2, that's x to the 4, and then you do x to the 1, that's x to the 5. So this is what we should do when n is odd. Okay, so now we can code this and see if it's working. Okay, so this was still correct when n was even. Oh, I have to do this first. And remainder division with 2 is 0. So when n is even, that part is correct. Otherwise, return x times, I copy paste this solution for when n is odd. Okay, so let's see if that fixed it. Okay, my power All right, so we are still getting correct solution. We need to figure out if it has a better recursion depth, if it's still going to crash on, let's say, things like 5 to the 1000. Yes, Jason. Did you have a question?
No, you answered it.
Okay, so, all right, so we have a correct solution. Let's see if it handles better this. Okay, so here's the one that crashed the previous solution. All right, so here's the one that crashed the previous solution. Now it's working, we get a huge number, but it doesn't crash it. Let's try it on something bigger. 7 to the 2000, even that is working. What about something really bigger? 20,000, 7 to the 20,000 something. It's working, it doesn't want to print it because it would take 200 lines to print it, and so on. Okay, so it seems that even when n is about 20,000, we are still in business. We don't exceed the allowed depth or height of recursion. So what is the recursion height of this solution?
Log base 2 of n.
Yes, it's log base 2 of n. Why is that? What did we say you should look at? You should look at by how much your solution, or whatever, your input size, in this case, n is what we are working, determining how many calls we are making, is going down in your recursive call. In each recursive call, is going down by 2. In each of them, you divide by 2. And when do you stop? When you reach 0. So you start with n, you divide by 2, you get n over 2, you divide by 2, you get n over 4, you divide by 2, you get n over 8. So you're dividing, you're asking how many times can I divide n by 2 before I get something, in this case, 0. So that's log base 2 of n roughly. Okay, so the height of recursion here, we managed to improve a lot, exponentially. We could do 2 to the million, and there would be only about 30 functions. Height of recursion would be about 30. And in the previous solution, it would be million, except that it would crash when it gets to 1000. Okay, so the height of recursion in previous solution was n, and in this one is about log n. Okay, all right. So is there something, by the way, so let's look at this. So we figured out recursive solution, correct. We figured out height of recursion, and we even improved it. Okay, so let's now talk about number of operations. So classical solution, the first one we heard, and the one that you were taught in school, and the one that you heard was, you want to compute x to the n. You just multiply x n times, like 2 to the 100, you do 2 times 2 times 2 times 2 times 2 times, you do it 100 times. So this is iterative solution. Let's do it. Okay, so let's write iterative, meaning solution with a loop without recursive calls. Let's compute that one. So how do you do it? First of all, you set the result to 1. Okay, that's before you even start. And then you repeat n times. Then you repeat n times, you multiply by x n times. So you take p, it was 1, then you multiply by x, and that becomes your new p for a product, okay? And then you multiply that p again by x, multiply by x, okay, return p. Okay, so that's a solution without, I'm gonna get you, Francois, let me just, that's a solution without 2 to the, unless I have a mistake, no, without recursive calls. Okay, it's still a correct solution. What was your question, Francois? You muted.
If you have p equal to 1, why is this p times x is not equal to 1 again? Oh, never mind.
Okay, no problem. because I mean, when you do multiplications, you always should start with 1, not with 0, because then it's always going to be 0. So when you're doing when you're doing summation, what you start with is 0, and when you do multiplication, you start with 1 because it doesn't affect your result de facto. Okay, so this is just gonna, this is literally the same as saying do x times x times x times x n times. Okay, all right. So so now let's talk a little bit about back to the efficiency, right? So this solution here does, if you want to do x to the n, it does n multiplications, right? X times n multiplication. So what is the running time of this solution? Now we're going back to counting the number of operations. We're talking about efficiency, how long you're going to wait for the solutions. So this solution here, how many operations does it do? This one, it's just 1. Loop is executed n times. And here we have 1 multiplication, all right? But it's repeated n times. Okay, here we return 1 value. So we do roughly ON, we do roughly linear number operation. And specifically, we are doing n multiplications, right? Because doing x times x, we are doing n multiplications. So we are doing at least n operations, n multiplications. Okay, so let's go back to this solution. This one is kind of difficult to analyze because we have so many function calls, and I don't want to analyze this one. I can tell you that this solution, this one here, the way it is written right now, also does n multiplications because it has so many function calls. Each one of them is, I don't want to draw this, it's going to look like a tree, these function calls. And I have only 5 more minutes and I want to show you something else. Okay, so here. Look at these 4 function calls. We have here 4 function calls. In fact, because you're going to do either this or that, we have 2 function calls, these and these. But when you're looking at these things, here we're going to call twice this. We're going to call this function call. When it's done, we're going to call this function call. Does something bother you about this? So how is this? Go ahead.
Isn't there a function within the function?
Can you repeat?
Isn't there a function within our function, the integer division, that's a function?
No, that part is fine, but pay attention to these 2 things. First, this call is going to get executed and it's going to do lots of operations, okay? And it's going to give us a result fine eventually. Then we're going to make this call. But do you notice something? Compare this call to this call.
It's the same call.
It's the same call. Why would you call a function twice? What if that function does exponential amount of work and you just finally got your result? You're going to call it again, the same thing. If ever, that's the whole sole reason of existence of variable. If you're going to use something again, store it in a variable. Okay, so here we have these calls. These are all the same calls. Okay, so let's take it out and remember that result. Results. And now I can just do, I have that result. So I do that. Here it's result times result. And here also I do result times result. Okay. All right. I'll be with you in a minute, William. So this looks like a trivial change. All right. But in terms of efficiency, does anybody know, can you tell me now, how many operations, more specifically, let's say even how many multiplications? So the other solution, iterative solution to compute x to the n, does n operations. And that seems, how do you even avoid it? You do x times n times. You need to do that, okay? Well, how many multiplications does this solution do? Anybody? I'll take William's, while you think about it, I'll take William's question and then anybody can speak. What's your question, William?
Why can't we do res squared?
You can do
know, for
res
res-
square, but res squared is, it does res time res. You can do res squared.
Oh, okay.
Yeah.
Thank you.
We can do it. It's equally, it's the same thing. We can, definitely. Let's go back to the number of multiplication. To compute x to the n, how many multiplication does this solution do?
Log n.
It does log n. So we are doing exponentially less multiplication. So for the end of the class, I will actually show you that on an example. Okay. Let's end it on an example. So let's try it. Let's have a call my power function where x is 2 and n is 8.
We can't see your screen.
Oh, yes, thank you, thank you. There you go. So let's say we had a call to my power function with x2 and n is 8. So the power is 8. And you will see that you're not doing 8 multiplications, hopefully, but you will see where it happened. Okay, so we start here, n is not 0. We have immediately this line. So this is a key line. We get to the line where we have result is equal and we have a function call. So this function pauses and calls another function and it passes x again and it passes n over 2. X is 2, sorry. So I might as well put that. X is 2 and it passes n is 4. So this function pauses and this one starts running. N is not 0. When this function is running, n is not 0. It's in a highlighted line. It gets to highlighted line. The result is, and we have a function call. So this function pauses and a different function starts running. This one here, where x is 2 again is passed and n is n over 2, which n this n. So that's 4 divided by 2, that's 2. That function starts running, and that one too, since n is not 0, immediately gets to the highlighted line, and you get result is equal. Oops, we have a function call again. So this one pauses, and this one starts running. In that call, we pass x is 2, and n is n divided by 2, which n, this n, or function that was just running, 2 divided by 2 is 1. Okay, so this function starts, n is still not 0. We come here again, we hit the highlighted line. We have a function call. Therefore, this function is going to call that and pause. What does it pass in that call? X is 2 and n is n was 1 divided by integer division by 2, n is 0. So this one now starts running. Finally, we reach 0. N is 0 again. Okay, and we reach n is 0 again. So finally, we start returning. So this function says return 1. It returns 1 to the caller. It was waiting in the highlighted line. It returned 1. So finally, that one has a 1 for the result. And we are in the case where n is the function that's currently running, n is odd. So we come to this case here. We need to return what? X is 2. So 2 times result times result. So we need to return 2. So this function is going to terminate and return 2 to the caller. So this function terminates and returns 2 to the caller. Therefore, this function can resume. So we now know that the result is 2 here. The res is 2. So this function with n is 2. This function with n is 2 can resume. And n is even, so it just returns res time res. That's 2 times 2, that's a 4. So this function returns 4. And to the caller and terminates. The caller can now resume. It was the function with n was 4, and we returned 4 here. N is even, so we need to do return result times result. So 4 times 4, that's 16. So this function returns 16 and terminates. So it was 16 that was returned. Now the first function that we have, the original one, when n is 8, can resume. We are in even case since n is 8, so we return 16 times 16, which is whatever. Okay, so we are done. And what was the number of multiplications that we did? I don't know, 5 or 6 or something. Anyways, this should be less than 8, or at least it will be less than 8 if I did 2 to the 8, 2 to the 16. You're going to start seeing the pattern that it's actually log base 2 of n number of multiplications that we do roughly, or basically number of operations. So this solution, this last solution that we have, both has it has a really good height of recursion, which is log n. Remember, if you're computing, if n is billion, your height of recursion is like 30. And it only is performing log n number of operations, which is much better than what we get in this obvious iterative solution. Surely you can do this, so you can implement this also in iterative solution, but it's not as obvious. This is, I find, again, this is much more natural, but depends on what you're used to. Okay, so we are at the end of the class.